Alright, so in this video we're going to talk about the derivatives of logarithmic functions. So that's stuff like ln x or base a log of x. So just a quick refresher on logs. First of all, ln x, what's that? That's the natural log, right? So that means the base e log of x. And what's that number e? Well, that's the irrational number. It's about equal to 2.718281828. And it looks like it's going to start repeating, but it doesn't. I think the next digits are 4, 5, 9. I think maybe a 0, I don't know. Anyway, it's an irrational number because the decimal representation, it never ends and it never repeats. So this number is irrational. But we can actually define it exactly. There are actually a lot of different ways of defining e, but one way that's especially useful in calculus is as this limit. So this equals the limit as n goes to 0 of the quantity n plus 1 raised to the 1 over n. Alright, so we're not going to evaluate this limit, we're just going to take this for granted. It's pretty much a definition, so we can just assume that. And there are ways to evaluate this, but they're kind of a little more advanced, and it's a topic for a much later video. But anyway, this is one of the definitions of e that's especially useful in calculus. So, you can see if you try direct substitution, what do you get? You get 1 to the 1 over 0, and that's kind of weird. But anyway, this limit's exactly e. So, more generally, you could have a base a log of x, and in order for that to make sense, a has to be positive and not equal to 1. Alright, so I just want to point out real quick that when you're dealing with like math and engineering and stuff like that, really the only log that matters is kind of the natural log of x here. And the reason is, well, first of all, you could take any log you want and rewrite it as a multiple of the natural log. So remember the change of base formula from your pre-calculus days. If you have the base b log of m, that's the same thing as saying equal to the natural log of m divided by the natural log of b, right? And this doesn't have to be natural log, it could be any base you want. So remember the change of base formula says you could take any base b log you want and just rewrite it in terms of any other base you want. And specifically, you can rewrite it in terms of a natural log. So b is just some constant, right? It's some positive constant not equal to 1. So ln b is some other constant. So really what we have here is a constant multiple of natural log of m, okay? Because that's like saying 1 over ln b times ln m. So just a constant multiple of natural log of m. All right, and that's actually kind of where this formula comes from. So what we're going to do is prove this one, and then we'll see that this one follows directly from it using the change of base formula. But we'll show all that when we get there. So anyway, if we could use the change of base formula to rewrite any base log as any other base, why the natural log? And the reason is, the natural log has this base e, and this number e is probably one of the most important numbers in all of math. It just shows up everywhere, pretty much anything you can think of. It's just incredible and amazing how it just shows up in all these applications that are otherwise so seemingly unrelated. But anyway, let's get back to the topic at hand here. So let's say, let f of x equal natural log of x. And we're going to show that f prime of x equals 1 over x. So it's a little bit lengthy, but we'll get there. And I think it's pretty interesting, this process. So f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x. Okay? All divided by h. So this equals the limit as h goes to 0. If f of x is ln x, then f of x plus h is just ln quantity x plus h. So this is ln quantity x plus h, and then minus f of x, all divided by h. All right. So now what we're going to do is write it like this, limit as h goes to 0 of 1 over h times what? Well, here, natural log of something minus natural log of something else. Remember, one of the properties of logs says that if we have ln a minus ln b, then that's the same thing as saying ln a over b. right? As long as a and b are valid things that you can take logs of, we're not going to worry about that here. So this a difference of logs equals a log of a quotient. So we're going to use that property here. So here, natural log of this minus natural log of that equals natural log of this over that. So natural log of x plus h all divided by x. All right. Okay, so now we have that. Square brackets, not really necessary, but not a bad idea. So now let's go ahead and simplify that. Let's come up here. Let's erase this. Let's separate these just to make everything easier to read. So this is going to equal the limits as h goes to 0 of 1 over h times natural log of here x plus h all over x. So that's going to be x over x plus h over x, all right? And x over x is just 1. So let's go ahead and write that as just 1. Okay, so this is what we've simplified everything to so far. So now we're going to use another property of logs in the next step. So this other property that we're going to use, it says that r times the natural log of x equals natural log of x to the r, like that. So in other words, factors being multiplied by the log can be brought up as powers, okay, inside here. So we're going to apply this to this. So this is a little bit messier, but we can still use this property here. So we're going to take this 1 over h and bring it up as a power of this whole thing in here. All right, so what we're going to have, let's erase that. And this is going to equal the limits as h goes to 0 of the natural log of 1 plus h over x, and then all that's going to be raised to the 1 over h now, because we're going to bring up this factor as a power. All right, so that's what we got going on here. And limit as h goes to 0 of all this here. So these big round parentheses I drew and the square brackets technically aren't really necessary, but again, as usual, always good to have those to be as clear as possible. All right, now things are going to get a little bit tricky, but not too bad, I guess. So now we're going to make a substitution, because what we actually want to do eventually is use this fact here. We want to use this somewhere eventually. So, you know, we kind of see that what we have here is starting to resemble that a little bit, right? Here's 1 plus something raised to 1 over something, you know, 1 plus n raised to 1 over n. So now we just got to modify this a little bit so that we could use that up there. All right, so the substitution we want to make is this. Let's say n equals h over x. All right, so we're just going to make this substitution. We're going to take h over x and just call it n. All right, so this we're just going to take it and we're going to call it n. All right, so now you've also got this 1 over h. What are we going to do with that? Well, if n equals h over x, then what does that mean about h? That means so h equals n times x. All right. So we're saying n is h divided by x, so that just means h equals n times x. So 1 over h actually becomes 1 over n times x. So this becomes 1 over nx, like that. Okay. H is nx, so 1 over h is 1 over nx. So we have that. Now one more thing we have to change. Basically we're just going to convert everything with an h to something with an n. So here we're taking a limit as h goes to 0. Now we have to change that to a limit as n goes somewhere. Well, if h goes to 0, where does n go? Well, h is going to 0, n equals h over x. So if h goes to 0, then n goes to 0 over x. What's 0 over x? It's just 0. So n also goes to 0. So in other words, let's come up here because we're kind of running out of room. As h goes to 0, n equals h over x goes to 0 over x, which is just 0. So in other words, n goes to 0 is what that means. Okay? So that's what's happening there. So now let's erase this stuff over here and rewrite our limits using what we just did. So now that equals, let's maybe get rid of this too. That equals the limits as n goes to 0 now, right? We're going to change everything into n. As n goes to 0 of the natural log of 1 plus n to the 1 over nx, right? Of 1 plus n to the 1 over nx, like that. Okay, so that's our new limit here. All right, we can see we're almost there, right? You know, here's a 1 plus n to the 1 over nx, but what we really want is 1 plus n to the 1 over n. So we're pretty close, but still just a couple things we have to do. Okay, so what next? Well, here, 1 over nx, first of all, 1 over nx, that's the same thing as 1 over n times 1 over x, right? So let's go ahead and rewrite this like that. So this is 1 over n times 1 over x. All right. Now we're going to use this fact here. If you have x to the ab, then that's the same thing as saying x to the a, and then raised to the b like that. Okay, so you know, if you have exponents being multiplied like that, then you can just rewrite that like this. So we're going to use this property up here. Let's go ahead and leave this one as it is, and then we're going to say equals the limit as n goes to 0 of natural log of 1 plus n to the 1 over n. All right, and then this is going to be all to the 1 over x now. And we got to be careful because we're actually taking a natural log of all of that stuff that we just wrote. Okay, so natural log of all of that. All right. And I'm not putting parentheses around the whole natural log because that's going to be too many parentheses. But you know, if you want to do that, that's totally fine. Okay. So now we're very close. We're almost there. What we want to do now is use that same property that we used before, actually, where we said r times natural log of x equals natural log of x to the r. But now we're going to use that in reverse. So here, what do we have? We have natural log of this whole mess in square brackets. Here, all that being raised to the 1 over x. Okay, so because we have natural log of this whole mess being raised to 1 over x, we can pull the 1 over x out as a factor. So let's go ahead and do that. And when we do that, what are we going to get? We're going to get equals the limit as n goes to 0 of 1 over x is going to come out, so it's going to be 1 over x times the natural log of 1 plus n to the 1 over n. All right, now let's go ahead and put these in here. Okay, so now we've simplified it to that. So we're very close. There's actually only 2 major steps, I guess. One of them's probably not really that major. Here, 1 over x. X is our variable, right? But as far as this limit is concerned, x is a constant. And what do I mean by that? Well, here the limits, you know, it's the limit as n goes to 0. So this limit only depends on n. So if we have an x floating around here by itself with no n's attached to it, then we could just pull it out of the limit, okay? So remember, we know that we can pull constants out of limits, and this is a limit as n goes to 0. So as far as the limit is concerned, x is just a constant, okay? Because the limit depends on n and not x. So whatever x does, the limit doesn't care. It only cares about what's happening with n. So we can pull 1 over x out of the limits. Again, because the limit does not depend on x, it depends on n. Okay, so we have that. 1 over x times the limits as n goes to 0 of natural log of 1 plus n to the 1 over n. All right, so that's what we have so far. Now there's really one more major step to do. So let's come up here and do it. All right, so what we have is this. So let's actually just rewrite that up here so we can see both of these at the same time. So this, rewriting the same thing, we just have 1 over x times limits as n goes to 0 of the natural log of 1 plus n to the 1 over n. All right? So now the trick here is natural log is a continuous function, and what we know about continuity is that if a function is continuous, then we can push the limit inside of it. So this is the same thing as saying 1 over x times the natural log of the limit as n goes to 0. All right, of 1 plus n to the 1 over n, like that. So let's actually make these square brackets. Then this will be parentheses out here. Okay, so in other words, what we just did was we took this limit as n goes to 0, we just shoved it inside of the natural log. All right, and we can do that because natural log is a continuous function. And continuous functions have this property that limits can be pushed inside of them and pulled out of them. So we kind of briefly touched upon that in an earlier video when we talked about continuity. But anyway, we have this now. So what is this? Limit as n goes to 0 of 1 plus n to the 1 over n. That's this. Limit as n goes to 0 of n plus 1 to the 1 over n. Right? So this whole limit here, this is just e. All right. So what this really is 1 over x times the natural log of e. And what's the natural log of e? Well, that's 1, right? So that's just 1 over x times 1, or in other words, just 1 over x. So remember, this is our f prime of x, this whole process that we were doing here. So this shows that if f of x is the natural log of x, if f of x is the natural log of x, then its derivative is 1 over x, right? And that's how to prove that. So that was kind of a long process, but anyway, this is pretty much going to follow directly from that. So let's go ahead and see that just real quick. So we're going to use the change of base property for that. Let's zoom out just a little bit. So if we have base a log of x, we can rewrite that as natural log of x divided by the natural log of a. All right, using the change of base property. And in other words, that's 1 over natural log of a times natural log of x. So base a log of x equals this guy over here. So if we want to take a derivative, so if we say d dx of base a log of x, then that's the same thing as saying d dx of 1 over ln a times ln x. But what's 1 over ln a? It's just a constant, right? Because a is just a constant, so natural log of a is another constant. 1 divided by the natural log of a is yet another constant. And we know that we can pull constants out of derivatives. So this equals 1 over ln a times the derivative of natural log of x. And we have just shown that this is 1 over x. So this equals 1 over ln a times 1 over x. And another way of writing that is like this up here, 1 over x ln a. So this equals 1 over x ln a. All right. So that's the quick proof, or the more general case here. But again, natural log of a is really the more important one here, or natural log of x. That's the more important function because it has that special base e.